not Julian on stage. Yeah, so Philipp, with very robust health, has managed to get here and didn't get sick, so we are very happy to have him here. And he will be talking about folk rendering in Enshrouded. Surprise.
Exactly.
Can we? And we now switch to the slides because we. And there we go. All right, thanks, and Philipp, you take it away from here.
Thank you. Yeah, hello everyone. Welcome to my talk. The fog is lifting. Volumetric rendering in Enshrouded. So yeah, here's the agenda for my talk. I will give a brief introduction to volume rendering first, and then I will take about our motivations and goal for the volume rendering rework in Enshrouded. After that, I will explain which different types of participated media we have and the data models. And of course, I will also explain how to volumetric render all this stuff, like fog, clouds, and water. And finally, I would like to end the presentation with a brief conclusion. So, okay, let's start with a brief volume rendering introduction. So we treat participated media as a collection of microscopic particles. When light travels through a medium, photons interact with the particles, and a change of radiance may occur. The radiance will be increased or decreased depending on the optical properties of the medium. There are three main physical phenomena, as we can see here. So the first one is absorption. So it's the reduction in radiance due to the conversion of light to another form of energy, mostly heat. Scattering is radiance heading in one direction and colliding with some particles, and then will be scattered into different direction. And emission is the light added from luminous particles. So as a ray passes through a medium, it might collide with particles and be scattered in different directions. So the first one is in-scattering. So it's the increase of radiance from other rays may be scattered into the path of the light of the current ray. And the second one is out-scattering. It's the opposite, where photons scattered in different directions away from the path of the current ray. Yeah, an important part of the in-scattering equation is the phase function, which models the directional distribution of the scattered light. So it's basically similar to a BRDF. And there are two popular phase functions in volume rendering. The first is the isotropic phase function. It's basically scattered light in all directions equally. And the second one is the Hennier-Greenstein phase function, where the isotropic phase function scatter light. Where light is scattered in different directions based on the anisotropy parameter G. So you can define how much light is scattered backward or scattered forward into the direction of the ray. So next thing is the extinction and transmittance. So extinction is basically the loss in radiance as the light beam travels through the medium. The extinction coefficient, sigma t, is the sum of the absorption and scattering coefficient we saw earlier in the slides where the absorption and scattering was presented. And the transmittance is a fraction of radiance transmittance from point P to P prime over the distance d through the medium, as we can see here. Yeah, so here's the full volume rendering equation. It looks a bit wild. So it's basically how the light decrement along the way, along the distance d from point P to P prime, heading into the direction omega. In the first part, the incoming light is reduced by multiplication with the transmittance. So that's basically the start of the ray before it enters the volume. And the second part is the accumulated emitted radiance due to emission from the media. And the last part is the accumulated in-scattering radiance of light from different directions scattered into the path of the ray. So, okay, that's enough math, I think. So let's dive into rendering. So we have a lot of integrals to solve in our volume rendering algorithm. And unfortunately, there's no analytic solution for inhomogeneous media, which means the medium properties varies over the distance d from point P to P prime. As an approximation, we can discretely sample the integral over distance d. So that's the blue dots there. to compute the transmittance, emission, and in-scattering gradients and accumulate them. Yeah, one frequently used rendering technique is called ray marching, where we approximate the volume rendering equation in a single loop per ray. Each iteration of the loop evaluates the media properties and the lighting at the sample point and accumulate radiance and transmittance. Another thing I recommend is the conservative integration scheme from the great 2015 SIGGRAPH presentation, physical-based and unified volumetric rendering in Frostbite. So that increased the quality of the integration a lot. Another widely used volumetric real-time technique is the froxel volume, where froxel stands for Frustum voxel. It works similar to ray marching, but allows better parallelization by using clip-space aligned volume textures as a cache for media properties and lighting. We still need an integration loop. So that's the yellow line over all froxels along the depths of the Frustum froxel pyramid. But it's a lot cheaper because we already pre-computed most of the data. The resulting radiance and transmittance is stored at each iteration, so that's a difference to the ray marching, in a volume texture to get a low resolution voxelized version of the integral for all view rays. We can sample this texture at any point in the view system to receive transmittance and radiance for the corresponding view ray. So let's continue with the next point on the agenda, but first let me say some words about our game Enshrouded. So Enshrouded is a survival action role-playing game and is currently in early access. The name-giving gameplay element called the Shroud is a very dense and dangerous fog where the player takes damage and can even die if he stays there for too long. We want the shroud to look dark and dangerous, and the shroud border must be clearly visible so that the player can avoid it, because it's obviously dangerous. So besides the shroud, we also have more volumetric effects, where some are gameplay relevant and some are just for purely aesthetic reasons. So here's a short video showcasing the volumetric rendering in Enshrouded. The video quality is a bit bad, but I think you can imagine how it should look like. So okay. So as I started to work on the volumetric rendering in Enshrouded, we already had an implementation, which was done by my co-worker Lucas. He had a presentation last year at the GPC called Volumetric Fog in Enshrouded, so you can have a look on the video for a complete overview. This implementation already supported different types of media, except water, which is a new feature, a brand new feature in Enshrouded. And the rendering was based on froxels for the near field and ray marching for the far field. It was combined with ray march clouds and pre-computed atmosphere on top. Unfortunately, the previous implementation had some problems. So we had plans to use the voxel fog for dynamic effects like low-hanging clouds or dynamic shrouds. The previous implementation used a static representation for the far field and was not flexible enough for us. And even if the performance was good, the image quality did not match our expectation. So there were numerous optimizations that came at the cost of quality. And some features like volumetric shadows were limited to a short range near the camera. Also, the resolution of the shroud varies over distance to the camera, which causes the appearance of the fog to change over distance. And a low sample count and heavily rely on temporary filtering led to stability problems during motion, under motion. So initially, we want to increase the flexibility of the voxel fog and try to develop a unified solution for all media, including clouds. However, this proved difficult because the different media have different visual requirements and scales. So therefore, we dropped this goal after the first iteration of the new system. And we also Wanted realistic detailed lighting, while the final image should be stable under motion, so that was really important for us. And even if the new system should be physically based, we want to allow some degree of creative freedoms for the artist to set up the stuff, because the shroud isn't physically at all. So, and of course, we have to support the new water feature. Yeah, let's dive into the data models we use for to represent the different media types. The first one is the shroud, which is modeled with voxels. Therefore, I call it voxel fog for the rest of the presentation. Yeah, for the voxel fog, our artist created individual voxel models and placed them in the world. During a conversion step, these high-resolution voxel models are sampled into 60-meter voxels and divided into equally sized tiles. For each tile, we store block compressed density and signed distance, where, by the way, we use the BC1 trick presented from, I don't remember the name, but yeah, it's the same trick we're using there from the Nubis Cube paper. And empty tiles will be omitted, and tiles with uniform content can be stored as a single value, so to save storage. And at runtime, the required tiles are loaded and cached into a model tile atlas. So, and instances of these models can then be freely placed within our world bounds and are linked to a media material with basically extinction and scattering albedo. Yeah, so we now need to combine the placed instances into a large seamless volume that can be fast and easily rematched. Also, so the instance also could be moved, so we have to regenerate all this information at runtime. For this, we use a sparse virtual texture that covered the entire playable area. So as you can see here, each of the blue boxes is basically a tile in the virtual texture. Yeah, the voxel size of this texture is also 60 meter, so we didn't support scaling of the instances. And it covered the entire playable area with a resolution of 640 by 192 by 640, which results in around 7-8 million virtual voxels. So yeah, the actual voxel data is stored in a tile atlas, where each tile has a resolution of 16 cubed voxels per tile. And each tile contains half a voxel border on each side, which is required for a seamless trilinear interpolation. We store multiple block compressed layers for each tile with BC1 signed distance, BC5 density and extinction, and BC3 scatter albedo and detail noise type. I come to this later. So the content is updated at runtime using compute shader. So there's runtime compression of the BC data. Our interaction texture has a resolution of 43 by 13 by 43, and each cell covers 240 cube meters. So that's because of the odd 15 cubed pixels or voxels inside one tile. And a single pixel in the interaction texture is a 16-bit value with a 15-bit atlas address, and 1 bit to determine if the tile is empty or not. The interaction texture is updated once a frame on the CPU. At the same time, we allocate newly required tiles from the tile atlas or free tiles that are no longer needed. We also detect which tiles need to be updated and schedule the work to the corresponding compute shader. And yeah, in practice, we found that many tiles have identical uniform content. So we detect these tiles and we use a single one instead. Yeah, because our voxel fog has a very low resolution compared to the gameplay representation and the source data, which is half a meter. We need a more accurate and recognizable shroud fog boundary to allow the player to avoid it. Yeah, to do it, we add another representation of the voxel fog in the first 64 meters around the player. We stored 2 signed distance fields, one for dangerous and one for deadly fog in 128 cube volume texture. And the distance fields are runtime generated using the high resolution fog and scene voxel data. And we generate the SDF on the GPU. using a technique called fast hierarchical 3D distance transform, followed by a single jump fluid path to compensate some errors that the hierarchical method introduced. Because we also take the scene voxel data into account, we got beautiful ground fog in the shroud for free. We also have the possibility to place dynamic fog volumes. The volumes are spawned by the VFX pipeline and can have either box or sphere shape. Optionally, a density texture could be used to add extra detail to the fog volume. And injected fog volumes are the only emissive media in the entire volume rendering pipeline. I recommend watching Luca's talk from last year to get into more detail about it. So what you see on the right, the code snippet is just the data that the VFX pipeline outputs into a structured buffer. Enshrouded has a full dynamic day and night cycle and a weather system with different weather phenomena. And the weather phenomena, like rain and snow, can occur locally on the map. So for the sky, we follow the classical pre-computed atmospheric scattering approach, where we generate several lookup textures at startup. To determine how much light reaches the observer through the atmosphere, we have a 2D transmittance lookup texture parameterized by height and zenith angle. We use the lookup texture for all sun and moonlight intensity calculations. For the sky color, we pre-compute MIE and relay lookup textures by ignoring earth shadows. We can reduce the, proposed by Brunetten, by Alex, sorry. We can reduce the dimension from 4D to 3D, which makes it way cheaper to sample. And we also found that multiple scattering and ozone are really important to create realistic results. And one more lookup texture is generated with the spherical integration of the skylight, and it's used mostly for cloud lighting. That was for the sky, but for the aerial perspective, so basically the atmosphere between the camera and the opaque geometry. We use the same mass and coefficients as for the atmosphere lookup texture computation. We also support MIE and relay scattering, but we are ignoring multiple scattering. To add more depth to the final image, and we would want to touch the atmospheric properties, but we want to have more artistic freedom and depth in the image. We add an high fog. Which is adjustable with an exponential fall-off and has some material properties like density and albedo. So for the cloudscape, the weather system renders multiple instances of artist-generated textures into a single top-down projected cloud texture, as we can see on the right. We also add some circle distortion to the texture. To simulate the curvature of the Earth, because the texture is top-down projected, and so we would like to have a nice curvature. The texture has two channels for density and height, and the resolution is basically 1K and covers 80 by 80 kilometers around the world center. We also want fog below the clouds where it rains or snows, so I call it weather fog in the rest of the presentation. This fog is rendered into 512 by 512 two-channel texture, projected top-down, and covers the entire playable area. It contains the density in red channel and the maximum height in green channel, so that the height is needed that it can end up where the cloud starts. The texture is runtime generated and derived from the weather system cloud and rain map. We also use a top-down projected variant shadow map to avoid fog and in buildings and caves. We also use this variant shadow map for our rain effects and stuff to avoid inside buildings. I will only briefly address water data model here. My colleague Andreas had a talk about it yesterday, so I'll just give a really short introduction. The water volume is stored in a sparse signed distance field where the distance is only present near the water surface, and the signed distance field is fully dynamic and interpolated from the water simulation step. And the water system renders the first view ray intersection with the water surface into a screen space texture. and this texture contains various information which could be then used down the render pipeline to check out if there's, for a certain pixel, if there is water or is it underwater, is the water surface hit, and stuff like that. Yeah, and finally, to add more details to the cloud in voxel fog, we use additional volume texture with tile-level detail noise. So the texture contains two variations of two noise types representing different cloud-like shapes. And the noise is generated, the noise generation is based on the SIGREF 2023 presentation used cubed. We configure the detail noise in our editor and generate it in our asset pipeline to just improve the turnaround times a bit. So, okay, so let's dive into rendering. So first we render a volumetric shadow map, a shadow volume, and a water shadow map needed to apply translucent shadows to volumetric and solid geometry. Then the scene irradiance is rendered using deferred shading. Also fog clouds and water volumetrics are rendered using different techniques. We compose scene irradiance, fog, and clouds to an intermediate texture and combine it with water afterwards. Shadows are important for realistic lighting. This also applies to volume rendering. Point and spotlights are very local, and we ignore the shadowing due to performance and memory reasons. For the primary directional light, which is either the sun or the moon, it depends on the daytime, obviously, we fill a 3D volume texture covered the entire playable area. The volume texture is very low resolution, with 32 meter per voxel and contains monochrome transmittance only. We use it for volume rendering and direct lighting as an addition to our cascade shadow map. To generate this texture, we launch a compute shader that sweeps through the volume in light direction. As you can see in the code snippet, it's a pseudocode. We first initialize our transmittance with cloud shadows and loop through each voxel along the light direction. We sample the media extinction from the voxel fog, high fog, and rain fog, integrate the transmittance and temporal accumulators with the voxel's previous transmittance. If the ray leaves the volume on one side, we reset the transmittance and continue on the opposite side. So in the slide before, it was a very simple example where the light comes directly from above and goes straight down, but in most cases it's more not that straight, so we can leave the volume on the other side. We also jitter the start position inside the voxel each frame using a Houghton sequence. We handle water transmittance differently because shadow volume resolution is very low and water needs color transmittance also. So to estimate the water depth for an arbitrary point, we render a camera-centered clip shadow map of the water surface. So we render 10 clip levels with 256 by 256 resolution each. And to avoid flickering under camera movement, we snap the center of each shadow map to light space pixel position. We can compute the transmittance from the water depth analytically by treating water as a homogeneous media. Because we render the closest water surface depths into our shadow map, we overestimate the transmittance in case of multiple overlapping water surface. So basically, it's the barely visible red part in the blue ray from the sun to the blue water surface, water volumes. So that's basically the amount we overestimate the transmittance. But in practice, it did not prove to be big problems because the water is mostly flat and also surrounded by solid geometry. So we have shadows, have solid shadows in most of the cases anyway. Okay, so let's continue with the fog rendering. So here's a simple diagram of the fog render pipeline. First, we combine screen space, water surface, and scene depths, which is needed for correct water fog compositioning. And we then render all fog types except voxel fog into a froxel volume. And last, we ray march voxel fog and combine it with the pre-integrated froxel volume during ray marching. So, but why do we use both ray matching and froxel volume and not only a single technique? So, yeah, ray matching allows high frequent details, but also needs some sort of empty space skipping and works best with dense media. And the froxel volume, on the other hand, is less detailed, but works well for less dense media like air and high fog. And yeah, combining the two techniques gives us best of both worlds. Okay, so let's start with the froxel volume rendering. Our froxel volume contains all fog types other than voxel fog. So the resolution depends on screen size and quality settings, and we cover the full view depth range from up to 10 kilometers. For performance reason and to avoid light leaking, we downsample the scene depth buffer to have an upper depth limit for all froxel computations. Yeah, because the world depth range is huge compared with the froxel volume resolution, which is basically between 96 and 128, or I think also 64 in the depths. We use a customizable logarithmic depth distribution to increase step length with distance. So, but the classic logarithmic depth distribution would be too dense near the camera. So we use a customizable logarithmic depth distribution which allows more control over the distribution by tweaking the factor k. Yeah, for our upper froxel depth limit, we downsample the scene depth to the screen froxel size. And to avoid artifacts during true linear filtering, we delayed the result with a 3x3 kernel. Yeah. So in the next step, we populate our froxel volume with media and light data. So we launch a compute shader with one thread per froxel and jitter the sample position by a Houghton sequence offset each frame. We then store scattering and monochrome extinction coefficients from all fog types except voxel fog and atmosphere in a texture. And the atmosphere is excluded here because ME and relay scattering needs colored extinction coefficient, and we output only a monochrome extinction coefficient in this pass. So we also store radiance from point lights, probe-based global illumination, and emissive fog in a second texture. In a third texture, we store visibility for our primary directional light by sampling the cascade shadow map and the volumetric shadow volume. All three textures are temporarily accumulated with the previous frame to smooth the result over time. We early out invisible froxels by using our upper depth limit from the froxel depth texture, as in the previous slide. For all the invisible froxels behind our depth limit, we write out NANs, so not the numbers, to the scattering and extinction texture. And this allows us to ignore invalid froxels during temporal accumulation because we get NANs back if we sample the last frame's texture. As a second step, we compute in-scattering and final extinction coefficients. So we again launch a compute shader with one thread per froxel and load the intermediate data from the populate step. Like in the populate shader, we early out if the froxel is behind the upper depth limit. We load the pre-computed data from the populate step for the given froxel and compute the atmosphere, Millet, and relay coefficients. Then we compute in-scattering for the primary directional light and the pre-computed radiance from the population step. Yeah, for the directional light, we multiply the pre-computed visibility and the corresponding phase function. So the resulting in-scattering and colored extinction is stored in two RGB textures then. Another thing, we do not temporarily accumulate these textures because the phase function is heavily view dependent, and this would lead to smearing and ghosting artifacts under motion. So last, we integrate the scattering and transmittance over the froxel volume's depths. We launch a compute shader with one thread per froxel on the XY plane. We first load the froxel depth texture and compute the iteration count of the integration loop. Inside the integration loop, we calculate the integration step length from the froxel slice index. And then we read in-scattering and extinction textures and integrating transmittance and radiance over the step lengths. So finally, we store transmittance and radiance in each iteration. So we store it in the same texture because we do not need the in-scattering and extinction texture anymore after this frame. And we have no contention there, so that works fine. Yeah. So next we have a look at our rematching pipeline. Because we may rematch in low resolution, we need some extra work to reconstruct the full resolution image. We first downsample the scene depth buffer to half resolution and choose 1 pixel in a 2 by 2 half resolution tile for the ray marching, which make the ray marching efficient like 1/4 of the resolution. Then we ray march the corresponding rays and combine it with a pre-integrated froxel volume. And finally, we reconstruct the half resolution image and upscale it to full resolution and tempera accumulate the result. So yeah, for all this, we mostly followed the approach from the 2019 presentation, creating the atmospheric world of Red Dead Redemption 2. I will not go too much into detail here, so please check out the presentation for a complete overview. So because we only march 1 ray out of a 2 by 2 half resolution tile, we must reconstruct the missing 3 rays from the previous frame. We reproject the missing rays and clamp in-scattering and transmittance history with the color AABB of the 5 by 5 neighborhood of the current frame. So we also weight the neighborhood pixels by the depth difference to prevent ghosting artifacts under motion. So basically to avoid that pixels that are too far away have effect on the AABB of the current pixels. So if the projection fails due to occlusion or at the screen border, we use the depth-weighted average of the pixels neighborhood. So it blurs the result a lot, but yeah, that's okay at this point. So that the reconstruction works, we need to place our array carefully in a 2 by 2 half resolution pixel tile. We want to cover the full depth range of the 2 by 2 tile. We have to find good positions for our arrays to march. So first, the depth buffer is scaled down to a half resolution using min-max checkerboard depths. And initial samples are placed based on the current frame index. So the initial samples change each frame, and it's also changing. It's also a bit offset in different in the 2 by 2 tiles of 1 frame based on a checkerboard. After the initial ray placement, a fixer pass detects isolated depth cases, so where some pixels couldn't be reconstructed in the final. Image, and each 2 by 2 tile so we detect isolated depth cases in each 2 by 2 tile and choose a different sample location in the case where we have isolated depth cases where some pixels couldn't be clamped correctly by the neighborhood. So this works fine in most situations, but however, there are still cases where high depth variance loads the flickering after reconstruction. Finally, we have to upscale the reconstructed image to full resolution and temporarily filter the result. So we're doing a 4-sample desired upscale of the reconstructed half resolution texture using a spatio-temporal blueness offset. And the kernel size of the filter is scaled by distance, so we avoid overly blurred fog in the far field. All samples are weighted by the depth difference to the full screen depth buffer to avoid wrong results by taking pixels into account that they're too far away from the original pixel. So the temporal filter is nothing special. During ray marching, we also output the transmitted weighted depths and use it for reprojection. We fetch history using a depth-weighted bilateral filter and clamp radiance and transmittance by a pixel's neighborhood color ABB. So yeah, let's start with the actual ray marching. So the ray starts at the camera and ends at the far plane or where it intersects geometry. We also compute the intersection of the ray with the voxel world volume and take this as a start or end if it's closer. Each grid cell in the graphics represents a cell in the voxel fog interaction texture. With gray boxes being empty and blue boxes containing some data. The gray dots are samples in empty cells, so we advance our sample position to the ray cell intersection. If a sample hits a non-empty cell, we continue with sphere tracing. We load the signed distance from the reference atlas tile and advance our sample position to the distance. For all sphere tracing samples, we max the distance with the minimum step length. This avoids very small or even negative steps. This is also from the Nubis Cube paper. The minimum step length increases over distance from camera. Yeah, so I think it's called adaptive sampling in Andrew Snyder's Nubis Cube presentation. So we check the sign of the distance to determine if the sample is inside or outside the volume, and samples with positive distance are outside, and samples with negative distance are inside. For samples inside the volume, we fetch density texture, density extinction, scatter albedo, and noise type from the world volume tile. Then we sample the detail noise from volume texture, from the detail volume texture, and lerp between the two noises based on the noise type from our world volume. To create the illusion of moving and wobbling fog, we scroll the detail noise texture into global wind direction and alternate between the two noise variations over time. We erode the voxel fog by subtracting the detail noise from the density. We then calculate the lighting for a given sample. For the primary direction light, we sample cascade and volumetric shadow maps, or the volumetric shadow volume. To add high frequency volumetric shadows, we take 4 extra voxel fog samples in the light direction for the primary direction light. So we mix 2 Hg phase functions, so Hg stands for Henry Greenstein, with different anisotropy to get better combination of fore and backscattering, which is a very common trick to do in volume rendering. And for the remaining lighting, we sample the radiance froxel texture generated in the populate step. The froxel radiance looks very flat due to absence of volumetric shadow, as you can see in the left image. This is mostly visible on the shroud surface if the directional light is fully shadowed. So to overcome the issue, we change ambient intensity and scatter albedo based on the uneroded fog density, which brings back some contrast in the surface region, like you can see in the right image. We also have to combine our samples with the pre-integrated radiance and transmittance from the froxel volume. So to do so, we first trilinear interpolate integrated radiance and transmittance from the froxel volume at our sample point. And we compute the radiance for the ray segment by subtracting the froxel radiance of the previous sample. We sum up ray march radiance and froxel radiance weighted by the transmittance of each other. Yeah, and we continue integrating samples along our view ray until maximum distance is reached, or the accumulated transmittance falls below a certain threshold. So finally, we output accumulated radiance and monochrome transmittance into a texture for the reconstruction step. So that's basically a trade-off because of the reconstruction. We only output monochrome transmittance, even if we have color transmittance. But yeah, we just take the luminance of the transmittance and output it. Okay, so let's continue with the clouds. We ray march one of 16 rays in a full resolution per frame. And the result is stored in a quarter resolution array texture with 16 slices. We also store the view projection matrix of each slice for later reconstruction. We reconstruct the full resolution image by reprojecting each full res pixel to a corresponding array slice using the stored view projection matrix. In addition to transmittance, we store directional light and ambient scattering intensity and multiply light, color, and phase function during reconstruction. So that's basically what you can see on the right. It's one slice of the array texture, and it just contains the directional light scattering intensity in the red channel, ambient scattering intensity in the green channel, and the transmittance in the blue channel. Yeah, so this is done to hide reconstruction artifacts if the light, direction, or color has changed during the last 16 frames. Yeah, so first we run a compute shader that generates a sky mask texture from the depth buffer to avoid computing cloud pixels that are hidden by solid geometry. And then we run the ray marching compute shader and early out rays that didn't hit the sky. We determine our ray start and end distance by intersecting two spheres with cloud layer start and end radius, basically representing our atmosphere, or the highs and end where the clouds start. And the sample count depends on the quality settings, and we learn between min and max sample count based on the length of our ray. We also early out the ray march loop if the accumulated transmittance falls below a certain threshold, like in the ray marching of the voxel fog. At each ray marching step, we construct the cloud density from the 2D cloud map and the sample's relative heights, as you can see in the upper image on the right. Similar to the voxel fog, we erode the density using the tile-level detail noise, which results in the image, in the lower image. For the directional light, we take 4 cloud samples into light direction to approximate volumetric shadow. So as proposed by Andrew Schneider in authoring real-time volumetric cloudscape with the Decima engine, we then combine 2 Beer-Lambert function to approximate multiple scattering. As you can see, the result in the left image. So the whole lighting is basically following the stuff from Andrew Snyder and the great Nubis paper. So in the center image, you can see the called powder sugar effect. We darken the cloud edges by multiplying the light with a factor based on the density of the clouds. We also decrease in-scattering at the bottom of the clouds, as you can see in the right image. And all these 3 will be combined together. So now we have our fog and clouds ready for compositing. So we launch a full-screen compute shader and fetch the scene irradiance and depth texture. If the pixel contains sky, we sample the atmosphere, look up textures for sun and moon direction. So that's basically the only place where we sample it 2 times for the sun and the moon to have better transition between night and day. We then reconstruct the full resolution cloud and multiply directional light scattering intensity with light color and phase function. For the ambient lighting, we multiply the ambient light scatter intensity with the additional atmosphere lookup texture containing spherical skylight integration. And then we combine sky and scene irradiance. Finally, we apply the full resolution fog texture from our ray marching pass by multiplying the combined scene irradiance and sky with the fog transmittance and adding the fog radiance. Okay, so last we have to render our underwater volume. So in contrast to other media, water has some interesting properties. So first, we have a visible interface between air and water, which prohibits us from rendering it together with other media like fog or atmosphere. Second, water could be treated as homogeneous, which enables some nice optimizations. And third, we define water as exclusive, which means we don't mix water with any other media because it's more dense than air or whatever. A very important visual effect we want to achieve are God rays. God rays are mostly visible where light abruptly changes due to shadowing or where light is bundled due to refractions or reflections. We want them to be sharp and high frequent in shadow border regions, and also want animated God rays caused by refracted light from the waves on the surface. So I first implemented a full-screen ray marching prototype, which already looks very promising, but was way too slow for a performance budget. It needs too many samples to capture the fine details we wanted. Using less samples and compensate this by temporal accumulation turned out to be not an option, because it will blur out the animated God rays too much and doesn't look good on email. So I remembered a paper about the technique called epipolar sampling introduced by Engelhardt and Dachsbacher in 2010. This is an optimization technique based on the observation that light shafts emanate radially from the light position on screen. the in-scatter radiance is mostly smooth along the epipolar lines in screen space. So we sparsely place ray march samples on the epipolar line and interpolate between them. So this drastically reduces ray count, but keeps the result sharp. Our implementation is inspired by Igor Yusuf's GDC presentation from 2013, and we use it for our primary directional light only. But how to place the sample? So first we have to find the start and end point for all epipolar lines on the screen. So for this we project our light on the screen. If the light is within our screen borders, we just use the screen space position start point for epipolar lines. If the light falls outside our screen boundaries, some of the epipolar lines will be completely invisible. The remaining lines need to be intersected and clipped against the screen border to find the start point, as you can see in the lower right image. The endpoints will be placed equidistantly on the screen border. We store start and endpoint pairs in a buffer for later use. For invisible lines, we store a large negative off-screen coordinate to detect them later. We now equidistantly place samples between each start and endpoint pair. Because our epipolar lines do not have the same length in screen space, some samples became too dense, especially if the light source is near the screen border, as you can see in the left image. So, to fix this, we scale the sample distance to be equal in screen space, where some samples could now be outside the screen and become invalid, like the red crossed in the right image. Oh, was it? Yeah. We launch a compute shader with one thread for all epipolar coordinate candidates. And for each sample candidate, we compute the screen space position and store it in a 16-bit lookup texture, where each row in the lookup texture corresponds to one epipolar line, and each column corresponds to one sample on the line. For invalid samples, we store a negative. Again, we store a negative off-screen coordinate, so that's black ellipses in the lower right. But this are still a lot of samples, and it would be too expensive to ray march all of them. So most of the samples are smooth along the epipolar line, which makes it unnecessary to ray march them. Instead, we choose some samples that will be ray marched, and all other samples will be interpolated from them. We first equidistantly place initial rays every n sample. We choose n to be 32 in our implementation. Then we place more rays where they are really needed. We test for depth, buffer, and shadow discontinuities and place additional rays on both sides of it. So each red dot in the screenshot is a ray march sample. You can see additional samples are placed at geometry borders, and also on shadow discontinuities on the water surface. We also place some additional samples near the light source to avoid shadow map flickering artifacts. That's the red, the more dense red samples around the light position on the screen. Here are some insights how the sample selection works. We run a compute shader with one thread per epipolar coordinate. We choose a thread group size equal the initial sample distance, so 8 in the slide graphics and 32 in Enshrouded. The first sample in the thread group and the last sample in the epipolar line are our initial rays and will always be ray marched. We test each other sample for discontinuity, so in the depth buffer or in the shadow map. If we found discontinuity, we atomic OR the corresponding bit in a group shared bit mask, and after a group sync, we check the bit mask and place rays on both sides of the discontinuity. Like you can see the yellow dots in the left thread group. We append all selected samples to a structured buffer where we store line and sample index, and we also atomic OR all ray march samples into a uint bitmask texture. So we need this texture later for interpolating the samples, the not ray march samples by the ray march ones. So the ray marching is straightforward. We dispatch indirected compute shader with one thread per ray. We march in light space and sample the cascade shadow map and shadow volume. And the underwater transmittance of the incoming light is approximated using the water shadow map. We also sample our animated ghost texture. where we increased the MIP level with increasing water depth to simulate some diffusion of the light. Because the Gaussian texture is not energy conservative, we have to multiply a normalization factor afterwards. We omit the phase function during ray marching because it could break due to linear interpolation. Instead, we apply it later in the compositing. The resulting in-scattering is sparsely written into an epipolar texture, as you can see on the right side of the slide. So basically, all the black is barely visible, but all the black areas are thin written, and the blue stuff is written by the ray marching shader. After ray marching, we must interpolate the remaining samples in the epipolar texture. We launch a compute shader with one thread per epipolar coordinate and early out all ray marched or invalid samples. For every other sample, we linearly interpolate from the two nearest ray marched samples. We search for the first set bit on the left and the right side in our bitmask texture. We output it in the ray marching path, and in the sample generation path, and linear interpolate the missing value and then store it in the same texture as our ray marched samples are stored. So we do not have any contention there. That's fine. Now we have an epipolar texture with our directional light in scattering, but we need to unwrap it into screen space. To do so, we first compute the screen space ray from the light position to the full resolution pixel, and then we find the two closest epipolar lines from which we will interpolate and project current pixels onto the line using the pre-computed start and end points. We now compute the UV coordinates and bilinear weights of the two nearest samples on each line. To avoid artifacts at depth discrepancies, we also compute bilateral weights from the depth differences. And after interpolating the final pixel, we apply the HG phase function. Because the epipolar texture only contains directional light, we still need to compute in-scattering from point lights and global illumination. So we ray march our froxel volume radiance texture that we written in the population path of the froxel volume in full resolution with a low sample count, and adds the result to the directional light. It's worth mentioning that we also clamped the length of all underwater rays by a maximum distance calculated from the water extinction coefficient. As last step in the volumetric render pipeline, we composite the water with fog and scene irradiance. For this, we render two full screen passes where the first pass is needed because of refraction through air-water interface. We also render the water surface during compositing. For more information, please check out Andreas' talk about water rendering and Enshrouded. But one thing is missing. How we handle transparent geometry. So we first separate transparent geometry in under and above water draws. For the underwater geometry, we multiply the pixel color by the analytic computed water transmittance based on the pixel's depth. Because we do not have any in-scattering for the given pixel. For the underwater, we fade out over the distance by multiply the luminance of the transmittance to the pixel's alpha value. For geometry above water, we need to combine it with the fog. Unfortunately, we cannot use the froxel volume because it don't contain the voxel fog. So instead, we try to approximate the fraction of fog to apply by using mean and variance from the transmitted weighted depths. We output from the ray marching path. But we are not quite happy with the solution because it's not accurate and it fails in some situations. This definitively is an issue, and we still need to do more work on it. So what did we learn from all this? So first of all, the volume rendering in real time is hard. So there's still a lot of trickery needed for real-time volume rendering, and I don't see that it will change that soon. So we also try to have a unified solution for all our different media types, but that would be really nice. But it doesn't quite work out for us. So another thing is temporal accumulation is not ideal for volumetric rendering because you don't have one point to reproject to the previous frame. But unfortunately, it's still needed. And sometimes it's hard to match the art direction and stay some sort of physically based. And transparent draw compositing definitely need more work and is a subject of ongoing research. And we also would like to integrate volume rendering in our global nation system. That's the last thing. But yeah, we haven't found a suitable solution yet. So, yeah, thank you for attention.